Hello everyone. Today we are going to learn about SSW and MSW techniques. So we will cover the overview of these two techniques. So uh, these are the outlines what we are going to cover. Why and where we can implicate the SSW and MSW techniques. What are the basics of their progression? Then we will explain about the SSW and MSW techniques. So there are various cases where we can see there are kind of soil strata variation where we need to estimate the stiffness of soil layer in terms of the shear wave velocity profile. In that cases, we are required to find out the how the soil layer stratification is going to vary along the depth. So in that case, we are needing to use the SSW and MSW techniques for estimating the shear wave velocity profile. So there are two assumptions which are implemented with this technique. First one is this soil layer should be horizontal. So it should be horizontal or plane surface, and the soil layer thickness should be constant throughout the depth. So if we have certain number of soil layer, so it should have some constant thickness along the depth. So these techniques will give the physical property of the soil, that is the shear wave velocity profile, shear modulus or density. So here we have these input parameters when we are in the process of estimating the shear wave velocity profile. So we will uh, going to have these kind of some parameter. First one is the thickness of soil layer, P wave velocity, and the shear wave velocity and density. So how if somehow we will know the density, then we can estimate the shear wave velocity using the shear modulus. So this shear modulus will provide the information about the stiffness of soil layer. And for a given Poisson ratio, we can estimate the P wave velocity. So first I will explain about where these techniques are going to use. So this SSW is a spectral analysis of surface wave and MSW is the multi-channel analysis of surface wave. So these two techniques are surface wave techniques which are used. So nowadays only MSW techniques are preferred, but the MSW technique is the updated version of SSW techniques. So the application is subsurface soil profiling, as I have told. So once we will estimate the VS of 30 meter depth, then we can estimate the average value of shear wave velocity up to 30 meters. So this will give the VS 30 of that particular site. Second one is that we can also estimate the bedrock mapping. So once we will know the VP, so VP will define the bedrock profile. We can also estimate the soil liquefaction potential that I have covered in another video. You can go and watch about the application of MSW. You will find how it is useful. Pavement characterization, shallow fault zone detection, and cavity detection. These are the some applications. So NHERP has given the guideline for a site. If your VS30 value ranges in these values, so you can classify your site based on this given guideline. So how wave propagates? So as we know, when there is any disturbance, so there will be energy. So energy will transfer throughout the body of Earth or surface. So in the meanwhile, in the common sense, we can say when there is disturbance, then there will be kind of propagation of wave on the Earth surface or inside the Earth surface. So if you will consider a huge mass of Earth, so that is if you will assume these are kind of homogeneous. So if you will place a boundary in between the homogeneous mass, then your energy will propagate or transfer throughout this boundary. So the introduction of a boundary is a continuum cause the propagation of the surface wave. So the waves are two types, body wave and surface wave, but surface wave is also two types, Rayleigh wave and Love wave. So these are if you have source and you will define the x direction here, y direction and transverse direction. So once the surface wave is going to propagate, so the relay will propagate along this radial direction. So retrograde motion is there for relay wave. In case of love wave, transverse motion is there. So this picture will give the some kind of visualization how this surface wave will propagate. Now the impulse or the source which you are going to apply on the surface of earth, so the wave is going to propagate. As I have already mentioned, the wave propagates as a retrograde motion, this surface wave. So these pictures, you have applied the load here and wave is propagating towards this. But how this is going to be dismissed along the depth? So that will be known as the how their strain energy is going to be dissipate along the depth. So, if you have smaller wavelength of your waves, so that will have the shallow penetration. If you have longer wavelength, so that will have the deeper penetration depth. So this is the very fundamental concept, and the wave which I have already mentioned, once it will going to propagate. So how it will propagate? So the surface wave and body wave both are behave in a different way in terms of their attenuation, how their energy is going to dismiss as they propagate. So in case of surface wave, the geometric attenuation function is there. So in case of surface wave, the geometric attenuation factor of surface wave propagating along the boundary of an elastic half space is proportional to the inverse of distance. And in case of body wave, it will attenuate 1 by r square. R means r is the distance. So the influence of body wave is dismissed earlier, but surface wave propagate for a longer distance. So now we will learn how and what kind of significance are there for spectral analysis of surface wave. So spectral analysis of surface wave is invented or it is studied 2-3 decades ago. So in the SSW techniques, the configuration of the two receiver was used and the impulse is placed at a some distance either from this receivers or either from this receivers. So and at the source point, the impulse is applied, and once the wave is propagated, and these receivers will capture the response, and that will be in the time domain. So here it is the source, and our receivers are placed in this direction. So we can change the configuration of placing the receivers. We can place the source either here or this side. It will depend upon the how we are going to implicate it. So this sensor response which we have gathered in the time domain, that will be converted in the frequency domain using this expression. Now we will see how the wave is going to propagate. So I am going to show you one kind of simulation of wave propagation. So here I have applied the load, and now you can see how the disturbance or transfer of energy is happening. So in this way, the wave is going to propagate, and the sensor which is placed here, they are going to capture the response of this ground motion or wave gate. So we have two sensors, and the two sensor is having the two response that we have already converted using the FFT, and that these two responses are in the frequency domain. So we can calculate the autopower spectra that is using this equation, and we can also calculate the cross power spectra. So cross power spectra will define the minimum energy below which there are high quality signal, and autopower spectra defines how the energy of each receiver is going to vary along the frequency. So the frequency distribution of energy of each signal will be determined by the autopower spectrum. And in the cross power spectrum, we can identify the predominant frequency present in the both the signals. So that is the cross power spectrum. Now there is another thing like how the phase is going to vary. So we can also calculate the phase of the cross spectra using this equation, and this wrapped phase is unwrapped using the unwrapping phenomena, which is done by the shifting of phase by the multiplies of two pi. So this unwrapped phase of CPS will give the linear pattern that will source the high quality of the data. If there is something in the quality of the data, that we can identify using the unwrapped phase. Now, once we have these phases, as we have calculated in the previous slide, and this delta x is the spacing of the sensor, and omega is the frequency. So we can calculate the phase velocity. Once the phase velocity is calculated, then we can also calculate the wavelength at that particular frequency. So this variation of the phase velocity or Rayleigh wave velocity along the wavelength is called the experimental dispersion. This experimental dispersion curve is further inverted using the some algorithm to estimate the shear wave velocity profile. So here the content which I have referred in this, the Occam algorithm is used for inverting the dispersion curve. So they have also compared with the approximation with the VS profile which is obtained from the approximation method along the inverted profile. So these are the overall game of how it is useful to have the shear wave velocity profile from the SSW technique. So there are some limitations, like here are only two sensors, so it is only applicable for the smaller array length, and it is having the time consuming. And next one is it will have the complicated interpretations. Suppose if there is a very thin layer, so that is not captured in this technique. Another is, it is having the issue of the spatial aliasing due to the sensor spacing. So spatial aliasing occurs when the wavelength of surface wave being measured is not accurately sampled by the sensor spacing. So what it will do, it will miss the high frequency component of the surface wave, so that will having the impact on the results. Now it is also having the some issue to resolve the multiple surface wave mode. So it is this technique is having difficulty in the filter the noising, and it is applicable for the shallow depth wave, and there is having near field and far field effect with this technique. Now how these limitations are like improved. So it is improved using the multi-channel analysis of surface waves. So in this techniques we have a multiple receivers that is placed in a linear array, and source is placed either in left direction or in the right direction. It depends. So if it is placed in the left direction, so it is called the forward shot. Once it is placed on the reverse shot, then it is called the reverse shot. So like for a given, as in SSW we can put the source, in the MSW we can also put the source in the same configuration. So here the 20 geophones G1 to G24 are placed, and once you will apply the load, the wave is propagating like this, and these are the wave field collected from this wave propagation. Now these are the MSW field equipment. Here we have these are the geophones, and these are the hammer and plate for the impulse. These are the connecting cables, and these are also cables which is used for triggering the geophones, source geophone. And this is the your control unit. We will call it seismograph, and this is the your laptop. So from the seismograph we can connect the laptop device to see the waveform when the data acquisition happens. We can also use another setup when there is a kind of very hard surface, kind of when you are going to apply this technique on the pavement, so we can use this kind of arrangement. Now this is the how these setups are going to be placed on the ground. So this is your source, and at an offset distance the geophones were placed in the linear area. So once the setup is ready, this is our setup which is ready, connecting with the data cables. These are the geophones. So we will apply the load at the source, and we will record the wave field using these devices. So this is kind of setup. Now these are the view of how the wave field is going to be collected from each geophone. So what we will do with this wave field? So this is the time domain signal of 24 receivers. So we will use the phase shift method to generate the dispersion curve. So in the phase shift method, you have your data in the time domain. So we will convert it into the frequency domain using the 50. Then we will normalize this wave response, and after normalizing, we will calculate the phase shift using this expression. And once the phase shift is calculated, then we will calculate the slant stack amplitude by multiplying the phase shift and normalized amplitude together for each receiver, and then we will add it. Then we will calculate the absolute value of this. Then we will get the normalized sum amplitude, where we can get the Rayleigh wave velocity and frequency variation. Right? Omega is equal to 2 pi f. So from this, we can calculate the dispersion curve like this. So this is the phase velocity, and these are the frequency, and these are the amplitude, wave amplitude, normalized amplitude. So the peak value of this normalized amplitude will be picked out. That is the fundamental mode experimental dispersion curve. So now once we have fundamental mode dispersion curve, then we will use the various techniques to estimate the theoretical fundamental mode dispersion curve. So for that we can use there are multiple algorithms. So this matrix method, which is presented by the Thompson and Haskell and Occam algorithm, and stiffness method of the Causal and Rosset. So how this Causal and Rosset stiffness works? So we have a optimized VS profile, or we can assume a set of VS and the corresponding thickness, and we will use the Causal and Rosset stiffness matrix to calculate the theoretical dispersion curve. The VS profile which you are going to calculate the theoretical dispersion curve, that should be more appropriate and the site specific, so that you will get the minimum misfit error between your experimental and theoretical dispersion curve. I will explain how simplicity in the understanding the experimental, theoretical, and theory profile. So you have experimental dispersion curve. So you have calculated the VS profile using the various optimization techniques. Then for the optimized VS profile, you will calculate theoretical dispersion curve. So from optimized VS profile to theoretical dispersion curve, it is forward modeling. Now from theoretical dispersion curve to experimental dispersion curve, there will be some similarity or comparison or L2 norm which you have calculated. That is the misfit error. So how it is done? So initially this black dotted line is the experimental dispersion curve, and then you have inverted VS profile like that. Then this VS profile is again used for calculating the theoretical dispersion curve, red one. So you can see there is a similarity, and the similarity is known as, or the similarity is calculated by the misfit error. So that is the L2 norm. Now these are the these are the process how we will calculate. So first we have the experimental dispersion curve, then we will calculate the shear wave velocity, then we can calculate the theoretical dispersion curve and compare how much it is similar to your experimental dispersion curve. So if you have multiple MSW tests in a single array line, so you can use the multiple VS profile to generate the 2D VS profile. So in a MSW study, the 2D VS profile is the variation of the soil stratification along the depth. So it is kind of mapping, contour mapping. So here you can see this 10 to 17. These are your horizontal length on the surface, and these are your depth, and the color bar will show you where is the stiff soil layer, where is the weak soil layer. Right? In this case, there is a high VS layer, hard soil layer, because it is having shear wave velocity of 500. Here at this location, you can see there is some kind of loose soil layer which is having shear velocity around 250. So this, I think you all have aware of how we will study the contouring of any map. So this 2D VS profile is only kind of contour plot with the variation of the depth and the distance, horizontal distance. So you will suppose if you have performed your test on a earth surface, so how the soil stratification is going to vary along the depth for some kind of stress along the depth. So if you will cut the earth, so how the soil variation look like? So that will be kind of the 2D shear velocity profile. So these are the few references which I have used for this presentation. So if you have any query in the SSW test, MSW test, or if you want to know further some kind of further information for these techniques, so you can contact me. We can discuss this later. The purpose of this presentation is to give some kind of insights to aware of these kind of techniques. So because this MSW technique is updated version of SSW technique, so there are various cases where you can apply the MSW technique. So another things I want to mention, if you want to know where this MSW technique can be used, so I have uploaded another video. You can search it, or I will provide the link of that video in the comment section or in the description. So the title of this video is Application of MSW Technique, where I have mentioned the practical scenario or the cases or the areas where you can implicate the MSW technique for the various objectives. So if you want to know about the application of MSW techniques, so you can go to that significant tutorials, and you can learn. You can make sure that like before applying the MSW technique, you should know where it should be applied. So that video is also helpful. Thank you so much.